Remind you where we are. So we looked at implementing this data structure called a stack, right? And so we've seen how to implement it using an array. In this class, I want to tell you how to implement it in a completely different way, so not using an array. And before we do that, I want to create an interface for our stacks because we're now going to have two different we'll have three different stack implementations, one using a list, one using an array, and the third one with the technique I'm about to show you in a few minutes. So we'll have three different stack implementations. They're all interchangeable because they all have push and pop operations. And so we'd like users of our classes to be able to pick the one that's best for them. So we're going to make an interface. We'll have all of our classes implement the interface, and then users can just use the interface on its own to define a type called stack. And then if they just use the interface, they can swap in whichever stack implementation works best for them. So to make the interface, right, again, you just create an interface called stack in this case. Right? So instead of a class, you make an interface. Now remember, an interface is just a bunch of methods, right, that have no implementation. So here, we're going to say that every stack will have a method called size. Right? So size is going to return the number of elements in the stack. Right? Now ignore this one for a second. I'll come back to this one in a moment. Right? And then we have push. Right? This is going to be a stack of strings. So not a stack. We did a stack of int in the last class. I'm going to do stack of strings now. So we're having a push method here, where you push a string onto the top of the stack, and we've got pop, where you pop the top string off of the stack. Right? So every stack implementation will have a pop, a push, and a size method. Now, there's a new method here that's got this word that we haven't seen before. So we have what's called a default method. Right? And also notice that the default method actually has an implementation. Right? So, before I told you that most interface methods have no implementation, it turns out you are allowed to implement default methods in an interface. Right? So here we've got our isEmpty method. Right? Now, if you're going to implement this method, the only methods you have access to are the other methods in the interface. Right? Because there is no class here. Right? There's no class that implements a stack. Right? There are no fields. Right? All you have are these methods, size, push, and pop. Right? So the only methods, or the only things you can do here, are call methods that are already in the interface. Right? So when I implement the method, I just is the stack empty? Well, if the size is 0, then yes, the stack is empty. Right? So I can actually provide an implementation for this method here. Right? So an interface is allowed to have default methods. Right? Now, classes are not allowed to have default methods. Right? So default methods, these only exist in interfaces. Default methods have an implementation, unlike most methods in interfaces. Right? And the implementation can only use methods from the interface itself. Right? Now, it turns out you can also use the methods from java.lang.object, but it's a little bit odd if you do so. Right? So because you can do that because every object gets the methods from big O object. Right? So if you happen to have an interface, a default method where you only need the methods from object, like toString or equals or hashcode or something like that, then you can implement it here. Right? And then you're also allowed to use what are called any methods from what are called the super interfaces of the interface. We're not really ready to talk about these yet, though. Right? OK, now you might wonder why an interface is allowed to have these default methods. Right? And it turns out in every version of Java prior to Java 8, there were no default methods. Right? So you'd have interfaces, the methods in the interfaces would have no implementations. There's a problem with interfaces. So as soon as you make an interface and you release it to the world, that interface is basically set in stone. Right? So in other words, you can't change that interface anymore. Because people are going to use your interface. Right? They're going to make a bunch of classes that implement the interface. Right? If you change the definition of that interface, everybody who used your interface now has to go and update their code. Right? And that's not a good thing, especially if you're providing the standard library for Java. Right? So it's impractical to add new methods to a widely used interface, right? Because everybody who's used your interface is now stuck updating their code. All right. Now, Java 8 added a whole bunch of new features to the language. And one of them was these things called lambda expressions, which we don't talk about in this course. But in doing so, in making this major update to the language and adding this new feature, the implementers of the standard library realized that they couldn't do this without adding a bunch of methods to many existing interfaces, right? And so now they're stuck, right? Do we change our interfaces that like millions of people have used now, right? Or do we not introduce this new feature, which turns out to be a very powerful new feature, right? And so they decided it's better However, we can introduce this new feature if we let interfaces implement default methods, right? And so the designers of the Java language decided that it was better to add default methods to interfaces rather than break everybody's existing code, right? And so that's why these things exist, right? And it's not unusual in long-lived languages like Java and C and now Python, right, that they acquire this stuff, right? So why do we have to add default methods? So you might ask, well, why didn't they have these in the first place, right? And the answer is because no one realized that they needed them in the first place. So it's not uncommon that as languages evolve, they acquire a lot of baggage, right? And this is one of the small pieces of baggage that the Java language has acquired. All right, so we already have an array list implementation of our stack class, right? So hang on, we can easily modify so that it implements it, but we can't do the same thing for array list. Oh yeah, okay. So our array list class, our array list-based stack, right? We can easily change that stack so that it becomes a stack of strings. Right? Oh, sorry, it's already a stack of strings. We made an array-based stack, but it's a stack of int, right? And our interface is for a stack of strings. So this interface isn't going to work for that array-based stack. We're going to fix all this in a little bit. Right. Okay, so let's go ahead and make our our list-based stack. Right. So I want to change our original list-based stack implementation so that it now implements the stack interface. Right. And it's easy. Right. So all you do is our list stack class, our previous class called stack now becomes list stack. Right. It implements the stack interface. Right. And all of the methods that were already there, well, they're also in the interface, so we're done. Right. So that's it. Very quick change, and we now have our original stack class now implements our stack interface. Right. So it's not a big change in this case. All right. So we can't quite update our array-based stack, but we will fix that in an upcoming lecture. So why don't we implement the stack now in the third way? So we're going to use these things called linked nodes. And this is quite different than anything you've probably seen already. Right? So for both the array list-based stack and the array-based stack, right, it turns out that when you push an element onto a stack, right, every once in a while that operation becomes big O of n. Right? So in the array-based stack, sometimes when the array gets full, you have to expand the size of the array. Right? An array list is just a list that has an array in it. So when the list gets full, you have to expand the size of the array. Right? Expanding the size of the array involves copying n elements, the n elements that are already in the list or array. So that takes big O n. Right? It turns out you can implement a stack so that push and pop are both in big O1 complexity. Right? So in worst case, it always takes a constant amount of time. Right? And O1 is a lot faster than On. So this seems like it might be a useful thing to do. Right? All right, so how are we going to do this? We're going to use these things called nodes. Right? And it turns out many classic computing science data structures represent some collection of elements. And the way they represent the collection is using these things called nodes. Right? So I'm going to show you how to implement a linked list later in the course. Right? When you take your data structures course, Cisc 235, right, you're going to run into these things called trees. Trees are just collections of nodes. Right? You may run into these things called graphs, which are also just a bunch of nodes. Right? Cisc 365 is the algorithms course, right? That will also tell you about graphs. Some of you might wander over to the math department and take Math 401, which is the course on graph algorithms, right? So there's a whole course that you can take that just talks about graphs, right? You could actually do this at the grad level too. All right, so what are these things called nodes? So conceptually, they're very simple, right? But implementing a data structure with them takes a little bit of time to get used to it. So a node simply stores an element, right, if it's a primitive type, right? So if I want to make a stack of int, right, then my node would have an int value in it, right? If you have a stack, if you want to make a stack that has where the elements are reference types, then you're going to have a reference to an element, right? And then the interesting thing with the node is that every node has a reference to 0 or one other node, right? So in other words, inside the node, there's going to be a field whose type is also node, right? So these references are called links. So it's easier to understand if I show you a picture, which I'll do in a second. Now, a stack is just a linear collection of elements, right? So by linear, I mean that there's a top element, right? And then underneath that, there's the next element. And underneath that, there's the next element, and so on and so on and so forth, right? So the elements are arranged in a sequence starting from the top element. Each element is connected to the next element deeper in the stack, right? So in other words, if you were to draw a picture of a stack, it looks like a line of nodes or a line of elements, right? So we call these type of data structures linear, right? So lists, for example, are linear data structures. Okay, so a node in our stack, right, is going to store, it's either going to store the element if our stack stores elements of primitive type, or it's going to store a reference to an element, and it's going to store a reference to the next node deeper in the stack. Right? Okay, so here's a picture of a stack using nodes, right, that has one element in it. Right? So here's our node, right? So the node is this whole thing here, right? So it's the box plus the arrow. Right? So here I'm showing you a stack. It's got one element in it, and it's holding one string, right? So it's got the string A on the top of the stack. Right? This looks like it's holding the string, but remember, it's actually holding a reference to a string, because that's the way Java works. Right? Okay, so there's our element. Right? So conceptually, you can just think of it as storing the element, which is fine. Right? So there's our element, and that arrow, that's our link. Okay? So element, link. So, oops, sorry. Element and link, right? Come on. Element and link. Right? So those are the two things that are in every node. All right, if I want to push an element on top of the stack, right, so what do we do? So I make a new node to hold the element that's being pushed onto the stack. Right? So I make a new node, and I'm going to store the string B in that node. Right? Okay, now every node has a link in it. Right? So I'm going to link that node to the old top of the stack. Right? So in other words, I'm going to link that node B so that it has a link to this node here, right? This link here is just a reference, right? So this node has a reference to the next node in the sequence, right? Remember, null means no object, right? So the old top node, well, there is nothing after it, right? So we use null to indicate that there's nothing after that node, right? And now you have to move top, right? So I'm going to adjust top so that it now points at the new node. Right? Now, top is just a reference too, right? So in other words, this dot top is just going to refer to whatever that node is there that we just created, right? And of course, we just added an element to the top of the stack. So if we're keeping track of the size of the stack, we add 1 to the stack size, right? So there's now 2 elements in the stack, right? So we can do the same thing again, right? I can push another element on top of the stack. So make a node, set the element to C, right? Link that node to the old top node, and then adjust the top reference so that it points to the new node. Right? Now, if I want to pop an element off the stack, what do we do? Well, I need to remember that there's a C sitting in this node. Right? So I need to obtain a reference to the element stored in the current top node. Right? So in other words, I need to remember, hey, the value here is C. Right? Whoop. All right. Now what do we do? Well, I'm just going to take top, and I'm going to make it point at the next node in the sequence. Right? So I'm going to make it point at the B. Now, how am I going to do that? Right? Because top currently refers to this node. Right? But that node there, that's got a link. Right? It has a reference to the next node in the sequence. Right? So I can just make top be equal to that reference, whatever that arrow is indicating. Right? And that adjusts top so that it now points at B. Now what do? Well, as soon as I move top, right, so that it points at a new element, there's nothing pointing at this node anymore. Right? So there's no reference to that node. Right? And so this node can eventually disappear, right, when the Java virtual machine decides it's time to get rid of it. Right? So it goes away. You subtract 1 from the stack size because we just removed an element from the stack. Right? And then you return the reference that you had in step 1. Right? So in other words, you return the reference to the C that we had way back in step 1 here. Right? Any questions about pushing or popping? All right. So the only trick to all this is how do I move top to the next node, right? And so the only trick here to remember is that, well, you've got a link to that next node, right? So I can always follow that link to the next node. Okay, so what's a node look like? Well, every node has a reference, right, to one element, right? So in this case, it's a string, right? Notice here I'm using aggregation, right? So a node is made up of one string, right? But it doesn't own that string, right? So it's not composition here, right? It's just aggregation. Right? So we have a reference to another string, right? I don't own the string. In this case, it's aggregation, right? Every node has a reference to the next node in the sequence, right? So every node has a reference to the next node in the sequence, right? Notice this is not aggregation or composition, right? It's association here, right? Now, why can't it be aggregation? Because aggregation is one way, right? So so in this case, a node. So in other words, a node does not own the next node that it points at, right? So it can't be aggregation. Okay, so how are we going to implement this thing? We're going to make a class called linked stack. Right? So this is going to be our stack that uses this linked sequence of nodes. Right? It's going to implement the stack interface, so it's going to have our 4 methods, size, is empty, push, and pop. Right? What information does it need in order to store these nodes? Right? So it needs to know, well, it doesn't need to know. It turns out you don't need the size, but it's convenient. Right? So it's convenient to know how many nodes are in this, or how many elements are in the stack, so that's the size. Right? And then all I need to store, I don't need to store all the nodes. I only need to store the first node. Right? I only need to store a reference to the top node because I can get to every other node just by following the links that each node has. Right? So I don't have a list of nodes. I don't have an array of nodes. I've just got the top node, right? The first node in the sequence. All right, now where's this node class? Right? So I'm inside the linked stack class. Inside the linked stack class, there's this node class. Right? So we've got another example of I have to remember what they're called. You have another example of a nested class. Right? Just like we did with when we implemented the range class, right, 2 lectures ago. Right? This one's a little bit different. Right? This class is static, right? And I'll explain what that means in a moment. Okay, so what's inside of a node? Well, there's a reference to an element. Right? So there's one string. Right? There's a reference to the next node in the sequence. Right? So every node has a node, right? Which is new. This is new, right? We haven't done this before, right? You've never made a point 2 that's got a point 2 object in it, right? But now we're creating a node class, right? Where every node object has a reference to another node. Right? The constructor doesn't really do anything. It just sets that value and that value. Right? So to make a new node, you specify an element, and you specify the next node in the sequence, right? And we just assign those values to elem and next. And that's it. That's your node class. Right? There's nothing else. Right? Okay, so what is a static member class? Right? So in the, I guess 2 lectures ago, I showed you something called an inner class. Right? So an inner class, which is not static. Right? If you have a static class that's inside of another class, then it's called a static member class or a nested class. Right? Or it's the simplest kind of nested class in Java. Right? Now, what's the significance of a static member class? So it's just a regular class. It happens to be defined inside of another class. That's all it means. Right? So if you just want a class that's defined in another class, a regular class that's defined in another class, then you make it a static member class. Right? Now, what's the difference? So what's the significance of making it static? Right? Because in the previous couple of lectures ago, the class we had wasn't static. Right? Now it is. Okay, so a static member class is not allowed to have access to the private stuff of the enclosing class. Right? So in other words, the node, right? Every node, so a node knows nothing about the stack that it's inside of. Right? So in other words, it doesn't, inside this node class, I can't access top or size. Right? So the node class has only access to the stuff that's inside the node class. Right? That's different than the inner class that we had from before. Right? The inner class from before, the inner class had access to the stuff that was outside of it. Right? It had access to the enclosing class. Right? In this case, you don't. Right? Now, what does that mean? It means that you can have an instance of your nested class, right, that exists in isolation from the enclosing class. Right? So in other words, I can make a node, right, and that node does not necessarily belong to any linked stack object. Right? So the node class is just a separate class. Right? It's completely separate from linked stack. Right? Okay. Any questions so far? So we're just going to use node as though it was a regular class, right? Okay, so what does the no argument constructor have to do? So it makes an empty stack, right? How big is an empty stack? Well, it has nothing in it, right? So its size is 0, right? If there's nothing in the stack, what is the top node of the stack? Well, there is no top node, right? So we set it to null. How do I get the size of a stack? Because remember, I have to implement size because it's inside the stack interface, right? So implementing size is easy, right? Our linked stack has a size field in it, right? So we can just return this dot size. So that's easy, right? Now remember, we have to implement push and pop. So how do I implement push? Well, you just go back to this a few slides ago, right? If I'm going to push a new element onto the stack, I make a new node, right? So there's my new node, right? You set the element in the node, right? Then what do? You make its link point to the old top of the stack, right? So I set the link of the new node to point at the current top node, right? So you set that, you set the next field of the node. Then you adjust the top of the stack to point at the new node, right? That's going to be easy to do too. And then we add 1 to the stack size, and that's easy to do too. Right? So how do you implement this? Well, it looks like that. Right? Make a new node. Right? So here's my new node n. Right? I make a new node. I want to store that value in the node, so I just pass it to the constructor. Right? Now, the constructor for node lets you set the link in the node. Right? I want to make this new node link to the old top node. Right? So you just pass in this dot top, right? And now your new node is connected to the current top node. Right? Okay, then what do? I have to adjust the current top node so that it points to the new node, right? So this top is equal to n, right? And now what? Increment the size by 1, right? So increase the size by 1, right? And that's it. It's actually very easy to do. All right, any questions on that slide there? Okay, how about popping an element off the stack? Right? So step 1, obtain a reference to the element stored in the current top node. Right? So I've got the top node, that's this dot top. Right? What's the element in the top node? Well, it's just this dot top dot elem. Right? So I can easily get a reference to that. Right? I need to make the top node point at the next node in the sequence. Right? So I want to make it point to B. Right? So how do I make it point to B? Well, this top just becomes this dot top dot next, right? Because that points at the B. So that's easy to do. Right? Decrease the size by 1. That's easy to do too. Right? And then return the reference obtained in step 1, which is also easy to do. Right? So popping the stack looks like that. Right? Ignore the exception for now. Right? Step 1, get a reference to the element that's stored in the top node. Well, that's just this.top.elem. Right? Step 2, move the top node down 1. Right? So this top becomes this top.next. Right? Decrease the size by 1. Okay, subtract 1 from size. Return the element that we got in step 1. So we return popped. Right? Now, remember that the stack should throw an exception if it's empty and you try to pop it. So is the stack empty? Right? If it is, throw an exception. Right? And that's it. There's your node-based stack implementation. Right? The only thing that you have to get used to is following these links around. Right? That's the only thing that's new here. Right? You just have to be, but you have to get used to doing it because it's weird the first few times you try to do it. Right? Right? So in other words, it's a bit odd to write, something like this top equals this top dot next. Right? What you have to remember is that top points to this node here. Right? So if you use top to access this node, right, and you access its next field, that gives you that link there. Right? And that link there just points at the next node. Right? So that arrow is really a reference to the next node in the sequence. Right? So writing something like this top equals this top next just moves top so that it points at the new node, at the next node in the sequence. Right? So instead of using an array where you access the elements of the array using an index, right, what you're going to do is you're going to follow links until you get to the node that you want to get to. Okay, so how do you implement toString for a linked sequence of nodes, right? So for toString, I want to generate a string that contains, that has the string representation of each element in sequence, right? So starting at the top, I want the string to have the first element, right? Then the next element, and then the next element, all the way to the bottom of the stack. Right? And so what does that mean? Well, it means I have to traverse this sequence of nodes. Right? And so how are you going to iterate over the sequence of nodes? Right? So the answer is, right, when you get to the end of the stack, right, the next node is null. Right? And so that's what you want to check for. Right? I want to start up here. I just want to follow the links until I hit a link that's null. Right? Because as soon as I hit a link that's null, I know that I've hit the end of the stack. Right? So starting at the first node of the sequence, right, you simply follow each next link to the next node until you reach a null node. Right? So this is the general pattern that you can use to iterate over a sequence of nodes. Right? You don't have to start at the top. Right? It could be the case you're implementing something and you're in the middle of your sequence. Right? So you start with a node, a reference to a node, n, right? And you just make it equal to whatever node you want to start at. Right? In this case, we're going to start at the top, but it could be some other node. Right? Then, while that reference is not null, right, that means your reference n is actually pointing at a node. Right? So you can do something with n there, right? You can use n.elem to get the element. You can do n.next to get the next node. Right? Once you're done processing that node, you just update n. Right? So n becomes n.next. Right? And away you go. Right? And that'll keep on going until n hits the, goes one past the last node in the sequence. Right? Now, whatever you do, right, once you hit this line here, right, n is going to be null on that line right there. Right? Because this loop runs as long as n is not null. Right? So on that line there, n will be null. And you can't use a null reference for anything. Right? So whatever you do, don't try to write n.elem or n.next here. You're going to get a null pointer exception. Right? Because remember, null means no object. Right? So you can't get the element from no object. You can't get the next node from no object. Right? So don't use n there. Right? All right, so toString. Oh, so this is the sequence. This is what happens. Right? So n starts out, in this case, pointing at the top node. Right? Is n null? The answer is no. Right? So process the C. Right? N equals n.next. Right? So n equals n dot next, right? So it now points at the b, right? Is b null, or is this node null? Sorry, the answer is no, right? So process the b, n equals n dot next. So n is pointing at the b, right? N dot next is that link there, which points at the a. So n now points at the a, right? Is n null? The answer is no. So process the a, right? N equals n dot next, right? Oh, now n's null. So I've processed all the nodes in the sequence. Right? So toString just looks like this. Right? So I'm going to start the string with the string stack, and then I'm going to print out the elements on separate lines. So it actually looks like a stack from top to bottom. Right? So starting at the top node, right? Here's my little loop, right? So while n's not null, do something with the sequence, do something with the node. Right, so I'm going to add a new line. So it's going to print stack, and then it's going to print the, it's going to give you the, it's going to have stack, and then on the next line it's going to have the top element. Right, so I'm going to append n.elem, and then I'm going to update n. Right, so n now goes to n.next. I'm using a string builder here, but you can just use a regular string. Right, string builder is somewhat more efficient if you have a big stack. Right, and then at the end, you're done. Right? I've processed all the nodes in the stack, so I just return b.toString to get the string representation of the string builder. Right? All right, any questions about iterating over a sequence of nodes? Right? It turns out that when you work with these node-based structures, this is all you end up doing. You just end up looping over these nodes. Right? Sometimes you start in the middle, sometimes you start at the start, sometimes you start at somewhere else. Right? Sometimes you have more than one node. You have more than one reference as you iterate over the sequences of nodes. Right. All right. There's something funny about the node class. Right? Every node has a reference to another node. Right? Until one node has no node. Right? So until one node has a reference that's null. Right? So the node class is an example of structural recursion. Right? So you know procedural recursion, right? Function calls another function. Here we have structural recursion, right? An object has an object of the same type inside of it, right? So every node has a reference to a node, right? That node has a reference to a node, which has a reference to a node, and so on, right? Until you end up with a null reference, right? If you stop and think about this for a second, right? You can imagine that any node that's not null, right, is the top node of some stack. Right? So what do I mean by that? Right? So the top of this stack is the C, right? But if I have a reference to this node, right, then that's a stack of size 2 where the top element is the B. Right? If I have a reference to that node, then that's just a stack of size 1, right, whose top element happens to be the A. Right? So every node you can just imagine as being the top node of some other stack, right? Of a smaller stack as you go down the stack. Right? Now if you stop and think about that for a minute, right, then you'll quickly realize that the fact that each node is recursive in structure means that you can easily write a recursive algorithm. Right? And so I can write toString recursively instead of iteratively. Right? So ignore that for now. Here's my recursive method. It's called toStringHelper. Right? So this is going to generate the string representation of a stack starting at node n. Right? It's going to generate the string representation of a stack starting at node n. Right? Now remember, that node is just the top of some stack. Right? So what's the base case for this method? Right? So the base case is, well, I know what the string representation of the stack is. Right? So if n is null, then that's a stack of size 0. Right? And the string representation of a stack of size 0 is just the empty string. Right? So there's your base case. Right? Okay, so what if the stack does not have size 0? Right? Then n actually points at something. Right? So how do I generate the string where it points at something? Well, I'm going to include the new line first. Right? Then I'm going to include the string representation of the element. Right? So that gives me the top node, right? The string representation of the top node pointed at by n. Right? Now what do I need? Well, I need the rest of the stack, right? I need the string representation of the rest of the stack. So how do I get the string representation of the rest of the stack? Well, I just call the recursive method, right? Passing in the top node of the rest of the stack. Right? What's the top node of the rest of the stack? Well, that's just n.next, right? And that's it. So there is another way that you can iterate over the sequence of nodes, right? You can iterate recursively over those sequence of nodes. Right? Now, I just have to start this method somewhere, right? So in my toString method, right, I'm going to make my string builder. Right? I'm going to get my reference to the top of the node. Right? And then I'm just going to call toString helper to generate the string representation of the stack, starting at the top node. Right? So this method recursively runs, generates a string. We append that string to the string builder, and then return the string representation of the string builder. Right? And so you can, when you have this type of recursive structure, right, you can either iteratively loop, right, or you can use recursion to do something with each node in the sequence. Right? But the key to using recursion is to remember that every node is just the top stack. Is just the top node of some other stack. Right? If you move further down into the stack, then your stacks keep on getting smaller and smaller and smaller. Right? Which is exactly what you want in a recursive method. Right? Now, when you're dealing with a linear data structure like a stack or a list or a queue, recursion normally doesn't help you very much. Right? Where recursion helps enormously is when you do Cisc 235. Right? When you learn about trees and graphs, you'll find that it's a lot easier to write a recursive method to visit the nodes in a tree rather than visiting the nodes in a graph. Right? So the trees you'll see in Cisc 235 look like this. So you'll have a node, and then normally you'll have two next nodes. Right? Those will point at a node. Each one of those might have two. Right? Right? And each one of those might have two, and so on, and so on, and so on. Right? So you'll learn about binary trees. You might learn about what do they call it? You might learn about general trees, where there's more than two per node. Right? But you'll definitely learn about binary trees. Right? So that's what you'll do in Cisc 235. Right? Now, when you look at that sort of structure, and you try to write an iterative algorithm on that, it becomes a lot harder. Right? But it's easy to write a recursive method on this structure, as long as you remember what I just told you here. All right. Any questions about a node-based stack? If you're a little bit unsure of it, just go back and review the pictures and the animations and translate those pictures directly into Java code in order to understand what's going on. Right? It's quite important that you understand how to do this, because we're going to revisit this concept at least twice more. Right? All right, I think that's a good place to stop for today. I think that's the end of this deck, right? Yeah, it's the end of this deck. Okay, so that's a good place to stop. And we will move on to the next part in the next lecture.